Chapter 12, uh, Deflection of Beams and Shaft, Part B, Moment Area Theorem. Example number 8. Let's consider we want to calculate the maximum deflection at the free end B for this cantilever beam at the free end B. So delta B is delta max. Mhm. And due to this non-uniform distributed load over the span of the beam, changing from 0 to L, from L to the support. So this is the fixed support. So if you calculate the moment at the fixed end, that's WL squared over 6, and that's just by making an integration about point A and convert the distributed load to a concentrated load of WL over 2 at the 1/3 of L from the base. So that's the whole length is L. So if you do so, that give you a WL squared over 6, as you can see on the figure. So let's see how we can calculate the mm, delta. So that's delta B, which is the maximum deflection of beam. Mhm. And also the total amount of load should be cancelled out by the only support at A, and that's WL over 2. And if you draw the shear diagram, it just start at the numeric value of WL over 2. And just goes all the way down to 0 because there is no force at 0. Mhm. That's 0. This is 0. And if you draw the moment, so this is a linear, this is second degree, and the moment is the third degree. So let's see how that goes. So we have the numeric value of shear, and if you just divide by EI, we have the M over EI for a moment area method. So that's WL squared over 6EA. That's the area under, that's the M over EI area. So if this is uh, linear, this is second degree, shear is second degree, and moment over area over EI, M over EI is a third degree curve. So if you remember in a third degree uh, quadratic spandrel, it's a 1 over n plus 2. That's a n plus 2. It's 3 plus 2 is L over 5. That's the centroid to the base. And the other one is a definitely 4L over 5. And for drawing shear and moment, a point is you need to look at the pattern of just let me make it clear. The numeric value of load is decreasing in load diagram. As you can easily see, the numeric value of load is decreasing. So it means the slope of shear should decrease. So if you look at here, this is the highest slope, and it just comes slower, slower, slower until it just reach to the slope of 0. As you can see here, this is a slope of 0. That's the load of 0. The slope of moment change to 0. That's the pattern which you need to draw. Numeric value once more. Numeric value of load is decreasing. That says the shear slope of shear. This is shear diagram. Slope of shear should decreases. until it reaches to zero because the load is zero at the top here. Mhm. And at the same by the same logic, numeric value of shear is decreasing. Numeric value of shear is decreasing, as you can again observe it here. Numeric value of shear is decreasing, so it means the slope of moment, that's m over ei, the slope of moment should decrease. So this is a decrease, decrease, decrease until it reaches all the way to zero. So numeric value of shear is decreasing until it reaches to zero at the free end of B. So it should, the slope of m over ei should decreases. So that's the highest slope. It decreases, decreases until it reaches to zero. And that's how you can easily draw the shear and moment and theta and delta diagram completely correctly. So, and delta B, as you can see here, delta B is just a tangential deviation of B with respect to A, with respect to A. And that's just based on second moment area theorem. It just says that's the area under M over EI, which is this part, which is this area, mhm, times times a distance from B. So that's a 4 over 5 L. That's here. That's M over EI from A to B, which says delta B is TB over A. That's a 1/4 of, that's a third degree in area is 1 over n plus 1, and in centroid 1 n plus 2. And that's BH. So our B is L, and our H is WL squared over 6EI. So that's a H, that's L, and that's 1/4 of B, LH or BH, times X bar 1. Hmm? And if you do the math, it gives you just, let me make it a bit cleaner. If you just do if you do the math, it gives you delta B is equal to a 1 over 30 WL to the power of 4. And that's a interesting result as well. So if you make a comparison between different beams, for example, we had the same cantilever beam, we have studied in a previous example. I will provide you. This is our example here. Let me double check it. Yes, yes, this is the same example. So if you have this cantilever beam, so handling this load, uh-huh, it just gives you a delta maximum of the 1 over 30 WL to the power of 4, which we just calculated. If we have the same beam, let's make a deeper look to the same beam with different loading. So if we have the same cantilever beam, but this time vice versa. So in previous problem, in our problem, the direction of load was like this. Mhm. And in this example, a bigger chunk of load is on the other side. So that was our problem, and it was a delta at B was W a 1, a negative 1 over 30 WL to the power of 4. Uh-huh. And now this time, if you just flip-flop horizontally the load, and the bigger chunk of load is it applies at the free end. So definitely by intuition, it might have a bigger, it gives you a bigger delta at B because it's a heavier part is on the free end. And that's correct. So what happened in this case, delta maximum is just a 1 and 11, negative 11, that's the direction, WL to the 4 over 121. One can say that's a almost a 1/12, almost 1 over 12. If you just consider this is as 10, this as if you just assume this is 10, that's approximation of 1/12 WL to the 4 over EI, and that's a far bigger than a the other scenario. Hmm? 1/12 in comparison to 1 over 30. And and at the same time, if you compare both of them to the same cantilever beam, but this time handling a uniformly distributed load of W all over the span. So if in such case delta maximum, it should be, if you calculate it, we already calculate, I will provide you with the link of that. That's a negative WL to the 4 over 8 EI. That's delta max. And it just brings us to an interesting conclusion of a comparison between the same beam with different with three different loadings. So let's see how is that. So the first one is uh, we call it beam one. So that's a condition that we have a uniformly distributed load. M is WL squared over 2, RA is WL, and delta is just provided to be WL to the 4 over 8 EI. And the second one is the same beam with the bigger chunk of load at the free end, but the notice here, you need to notice that this time the total amount of load is a half, because if you compare it with the scenario one, it's just missing this amount of load. So that's a W of mm, that's a half of WL, and we are missing another half in this part. But in this time, it's a just complete WL. So because we are missing this part, we expect to have a kind of lower deflection than the case one in scenario two. So and that what's that? That's a completely correct, and that gives us a also both the moment is smaller. So if you look at here, moment from WL squared over 2 a comes to a third, and delta max also goes by a almost a WL to the 4 over 12, and the exact numeric value is a 11 over 112 WL to the 4 over EI. That's just we round it up to mm, make it a bit more pronounced. And the last scenario, and also the load is goes by reaction goes by half. And the last scenario is just a uh, it's exactly case number two, but a flip-flop happened in loading. So this is the bigger chunk of load at the first part of the beam at the beginning, and this is the bigger chunk at the free end. So yet we anticipate to have a lower, even in comparison to, yet the load is the same. RA remains the same because both of them are should cancel out the total area under load, which is a half of WL. But the delta maximum in this case, it just goes by, even you can see it's a almost a um, 1/3 of even case 2. So it just comes from a 1/8 to 1/12 to 1/30. And that's interesting. And if you compare them, the delta max 1 is the highest, which goes for this one. Mhm. Delta max for the second condition, which has the bigger chunk of load at the end, goes by a almost 1 over 12. And the last one is this scenario. The bigger chunk is close to the support, and it just goes by a 1/3 WL to the 4 over EI. And that's interesting. Uh, if you make a comparison again in load, you can easily see load at the first scenario is bigger than the other, and the two, the second and third, are equal to each other in terms of load. In terms of moment, M for first one is bigger than the second one, MA in moment at the fixed part. and that goes by a w over 2, wl squared over 2, a 1, a half, a third, a 6. And the last part is delta for each of them. So delta 1 again goes by wl to the 4 over 8 ei. The other one is wl to the 4 over 12 ei, wl to the 4 over 30 ei. And that was a comparison between different of loading in the same cantilever beam. Thank you.